Okay, this is the lecture video for MAC1114 Trigonometry, and in this section we're going to be taking a look at trigonometric functions using the unit circle approach. We'll be finding exact values for various trig functions using a point on the unit circle. We'll also be finding exact values of the trig functions for quadrantal angles. We are also going to take a look and review special right triangles, and those will be inside of our unit circles. We'll be looking at the 30, 60, 90, the two special right triangles that you learned in geometry, and they may have come up in some of your algebra classes, 30, 60, 90, 45, 45, 90. And then we'll also be taking a look at how to use the calculator to approximate the values of trig functions. Okay, so let's get started with something that you're probably pretty familiar with. It does come up in a lot of your math courses prior to this one, and that would be the Pythagorean Theorem, which just states the relationship of the three sides in a right triangle. And you see a picture here where I've given you a right triangle inside of what we call a unit circle. So here's your right triangle. Notice that the two legs, we have a horizontal leg and we have a vertical leg. The name of this piece right here, as you probably well remember, is the hypotenuse. So the relationship between these three sides is the Pythagorean theorem. So it is the hypotenuse squared is equal to leg squared plus leg squared. Hypotenuse being the longest side is always kept on one side of this equation all by itself, while the legs are both on the same side. Everything is squared. So sometimes you may find yourself in a situation where you want to use this theorem in order to find one of the missing values on the triangle. To use Pythagorean theorem, you need to have been given at least two of the sides so that you only have one side left to find. Now, if we're applying this particular theorem to this picture, being that this right triangle is inside of what we call a unit circle, and a unit circle is just a circle with radius equal to 1. Okay, and much of your work is going to be a triangle inside of a unit circle. So that being the case, if we're going to apply Pythagorean theorem to this particular type of right triangle where the hypotenuse or the r value is equal to 1, the Pythagorean theorem then becomes leg squared plus leg squared. These are the two legs is equal to the hypotenuse squared. And in this case, the hypotenuse is a value of 1 because the triangle is inside a unit circle. Okay, other ways that you can find missing values on a right triangle would be the following. These are some definitions that go with this picture right up here. And these are how to find the values for the 6 trig functions that we're going to be working with throughout this course. Those are sine, cosine, tan, and then their reciprocal cousins, cosecant, secant, and cotangent. I've arranged these for you so that you can memorize those partnerships. Sine and cosecant are reciprocal cousins. In other words, the definition of this is the reciprocal of this. Cosine and secant are reciprocals, and tan and cotan are reciprocals. So let's go over those values. Now, I have written these definitions for you using just an R, but I also want you to consider how it turns into just this. So let's talk about that. Sine is defined as y over r. But in this case, since the r value is 1, if you were to put a 1 right in here, that would be y over 1, and therefore the sine value would just be y. So in the particular situation where you happen to be inside a unit circle and you know that your radius is 1, this definition becomes this. You will be in situations sometimes where the radius on your right triangle, or the hypotenuse rather, where that will not be a 1. And so you do need to know these universal definitions where you're just using an R. And so I've stated them for you here, as well as further into the section where we need them again, where we get into a situation where the R value is not 1. But if the R value happens to be 1, then this definition, y over R, becomes y over 1, or just y. For cosine, the definition is x over R. And because you're in a situation where the R value is 1, x over R becomes x over 1, or just x. Tan is defined as y over x. And y over x, there's no R value in here, so I can't replace any kind of an R value with 1, but I was able to do that here and here. You also need to have memorized who is the reciprocal cousin to who. So cosecant and sine are reciprocal cousins. Notice that one starts with an S, just so to help you memorize these. One starts with an S in this pair, one starts with a C. That is the same thing for this pair here. One starts with a C, one starts with an S. So that might help you not to mix secant with sine, thinking that they are reciprocal cousins. Okay, so sine and cosecant are reciprocal cousins. In other words, the definition used here, y over r, well, it's the opposite definition here. R over y. You're just reciprocal. If they're reciprocally related, that just means that you're going to flip this over. So it becomes R over y, in its definition. But again, since you are in a unit circle, your right triangle happens to be in a unit circle, and therefore the R value, the hypotenuse of this right triangle, which is also the radius of the circle, can be replaced by a 1. So R over y, which is a reciprocal of that definition, can be rewritten like this. 1 for the value of R over y. And that, in fact, is the way that we oftentimes state reciprocals. We take a value that we know is equal to a particular trig function, and then we just flip it over. So this became y when we put an R in there, and then if you flip that over, it's 1 over y. Okay, so again, let me just reiterate here. When your radius is 1, that is the only time that you can replace all these r's with the value of 1. So you have a much more simplified way of writing these definitions. Instead of y over r, just y. Instead of r over y, 1 over y. So just understand that you can take these universal definitions, which are going to also be used in problems where the R value is not 1, and you can replace the R value with 1 when you're in a unit circle. Cosine, this is the definition of cosine, x over R. But as stated, when you replace that with a 1, it's x, and this is the reciprocal cousin to it, which is just this definition flipped over. If you put the 1 in for R, then you get 1 over x. Tan and cotan, they are not impacted by the R value. It's just y over x for tan, the definition, reciprocal of that for cotan. So learn the reciprocal relationship so that you can just do the first 3, and then to get these 3 answers, you just can flip these 3 over and simplify, because you'll be asked to do that in a lot of the problems. Okay, we come to the first few examples, type of problems that you are going to be seeing in your homework. In fact, some of these, or these are a version of the type of problems that came directly from the homework software. So in the right triangle, example 1 says, with legs A and B, hypotenuse C, what would the Pythagorean theorem look like? Okay, well, the Pythagorean theorem goes like this. This is a way to write it when you don't want to write it with A, B's, and C's. You can start off like this. You can memorize this. It's always hypotenuse squared is equal to leg squared plus leg squared, which you often see it being written using A, B's, and C's. In this case, it says the hypotenuse is C and the legs are A and B. It's up to you how you memorize it. I like to memorize it like this, and then I plug in whatever variables they happen to be using in the problem. Okay, so if the legs are A and B and the hypotenuse is C, pick the answer. You're just looking for an answer that has C squared by itself. Hypotenuse always has to be on one side by itself, and the legs are together on the other side. Okay, so that would be this one right here. Okay. Example 2. If X and Y is a point on a unit circle in quadrant 2, what is the Y value? Okay, so we can make a little picture here. Okay, so if you're on a unit circle, don't forget the radius is 1. And they're asking you if you're over here in quadrant 2, don't forget this is called quadrant 1. This is how the quadrants are labeled, going counterclockwise. This is quadrant 1, quadrant 2, just to remind you, because you'll have to really have a firm grasp of that for many of the types of problems that we are going to be doing. Okay, so it says that you're in quadrant 2, so you're over here. It's like you're rotating. You have, remember from section 6.1, one arm stays fixed here while the other one rotates. So when they say that you're in quadrant 2, that means the rotating arm, called the terminal side, lands in quadrant 2. And the way these triangles come about that I've been talking about in this section is that wherever the point is that rotating side digs into the circle, come down to the nearest x-axis, and there's your right triangle. This horizontal leg will play the role of the x value, and it'll be whatever they've given you. In this case, it said that x is equal to -1/2. What is the y value? And because you're in a unit circle, you already know what the hypotenuse is. It's a 1. Just so you can get a visual on this, because when you can visualize it, it helps you understand it much better than if you're just popping things into formulas. And they want to know what is the y value. The y value is just the length of the vertical leg. So basically, you know, you're just using the Pythagorean theorem. And you know how that goes. We just discussed that in this problem right here. Hypotenuse squared is equal to leg squared plus leg squared. Your legs happen to be -1/2 and y, and your hypotenuse is 1. So hypotenuse squared is equal to leg squared plus leg squared. Okay, so now you have 1 is equal to y squared plus, you know that when you square a negative or a positive, it comes out positive. Squaring always produces a positive. You are squaring the top. -1 times -1 is +1. And you're also squaring the bottom, which is 1/4. Then you're going to take this to the other side. In other words, you're going to subtract 1/4 from both sides, and it would appear as a -1/4 on the left-hand side. So this is no longer here. I'll finish the problem up here. It's just 1 minus 1/4. You can put in your calculator if you need to, which is 3/4, and that's what y squared is equal to. But of course you want to give y, not y squared. And you do have to make a choice here, because when you solve this kind of equation, you take the square root here, you take the square root on the numeric side. And on the numeric side, there's actually both a positive and a negative root, but you're trying to decide, hey, based on the quadrant that I'm in, what kind of sign do the y values take on? Every time that you are above the x-axis, your y values are positive. And that's something that you probably are very well familiar with, but if not, I'm going to mention that to you. So your y value is positive, even though there are two different answers to this particular equation, you're going to stick with just the positive root. So square root, square root. Okay, don't forget that when taking the square root of a fraction, you take the square to the top as well as the bottom. So finishing that right up here, square root of the top of this fraction, just 3. You're not giving decimal answers, you're giving exact answers for almost every problem that you do. When they want you to give a calculator answer, which is just an approximate answer rather than an exact answer, it'll say approximate, or it'll say round to a particular decimal place, and that means decimals are okay. But here, no decimals. You're going to show that you know how to simplify algebraically radicals, fractions, etc. So square root of the top, 3. Square root of the bottom, 2. We're sticking with only the positive version of this root. So answer here, positive square root of 3 over 2. Okay, moving on. To example 3. Okay, it says find the values of sine of t, cosine of t. So they're just calling the angle created by this x and y coordinate. They're just calling that t instead of theta or alpha or beta. So they want you to find the value of all 6 trig functions for a point like this, and you are on a unit circle. Okay, and you can even get away with not drawing this because you basically have everything you need. The formulas that I just went over for finding sine, cosine, tan, cosecant, secant, cotangent, etc., they were made up of nothing but x's, y's, and r's. So if you want to try and do this problem without the drawing in a situation like this where you have everything right in the instructions, then you can go ahead and do that. Okay, so you have your x value here. They're just saying that this is a point right on the unit circle. You can draw it if you want to. I'm going to always give you a visual so that you can start to get comfortable with what you're actually doing instead of just kind of trying to visualize that. So basically what's happening is I'm looking at this and seeing that I have a negative x and a positive y. That just means that I'm rotating around the circle and I stopped in quadrant 2. Dug into the circle right there. And if you want to put these as part of a picture, the x value is 1/2. That's always the horizontal leg of this right triangle that you're creating. They happen to be calling this is called the reference angle, the angle created right at the origin. The y value, so this was negative 1/2. The y value is square root of 3 over 2, same numbers that I had in the previous problem. And they want to know what are the values for sine, cosine, tangent. So sine, now they call the t, typically when you're talking about a reference angle you have that little accent mark, but you can put either one there. Let's just put t. So just giving you kind of a visual of what's going on as you find these values so that you can relate it to the rotating that we did back in section 6.1. Okay, so there is a definition. And don't forget you're in a unit circle. That means the radius is 1, but the radius is the hypotenuse. So yes, this is the definition for sine, y over r. But since the r value is 1, it's really just the y value. And that y value is square root of 3 over 2. Okay, just going over the definitions with you. Cosine for any reference angle is defined as x over r. But since the r value is 1, it's really just x as the definition. So that would be, just the x value would be negative 1/2. Then we're going to do tan. These are the 3 basic trig functions. The other 3 are reciprocal cousins to this. So tangent of that angle t is defined as, here's the definition for tangent, y over x. And so that one's going to take a little bit of work. The y value, it's going to take a little bit of algebra and simplifying. So it's y divided by x. This is going to come up constantly when you're finding the six trig values. In other words, a complex fraction, a fraction within another fraction. When dividing, it is the same thing as multiplying by the reciprocal of the divisor. That's how you're going to simplify this, by multiplying rather than dividing, because these operations are equivalent. You can either divide by a number or you can multiply by the reciprocal. You're doing the same thing. Reciprocal just means flip the fraction over. It does not mean get rid of the negative. Put the negative wherever you want. Okay, that's the same thing. I call it float and flip. You're floating this up to the top and flipping it over. Okay, reciprocal. Okay, you're going to multiply by the reciprocal of the divisor whenever you're trying to simplify a complex fraction. Multiply by the reciprocal of the divisor. And just to memorize it, I called it float and flip. Okay, so there it is. It's not here anymore. I have floated that 1/2, that negative 1/2, up to the numerator, flipped it over. I see now that the 2's cancel, and that leaves me with a tan value of square root of 3 over 1, but with that negative sign. Okay, now you're being asked to find all six trig values. So we have the sine value, the cosine value, and we have the tan value. And now you need to find their reciprocal cousins. Reciprocal to sine is cosecant. So you're going to take that answer you got, flip it over. There's the reciprocal, and that would be a nice answer if you were allowed to give answers with radicals, but in the denominator, but you're not. You need to simplify, or what's called rationalizing the denominator. So you're going to multiply this by square root of 3, this by square root of 3. You're not to report your answers with radicals in the denominator. Okay, so this is going to be 2 times square root of 3. Enough room there. So 2 times square root of 3 at the top, and then just 3 at the bottom. That's your cosecant value. Okay, so you have your fourth answer. Then you're going to be finding the reciprocal to the cosine, and that would be called the secant. Secant is the reciprocal cousin to cosine. Reciprocal of that, easy, just flip that over, do not change the sign. There's your fifth answer. And then your sixth answer would be, what is the reciprocal to the tangent? Cotangent of t. Take that answer, flip it over. Again, remember, doing the reciprocal does not mean doing away with the sign, so that negative is still there. This needs to be rationalized, so multiply by square root of 3 on the bottom as well as the top, so that you're floating the radical up to the top. You're allowed to have a radical in the top, just not at the bottom, as far as simplifying rules go. And there are all 6 answers. Okay, you could have done this problem without the picture, but the picture will help you to understand how to draw your own pictures when the time comes that you actually need to do that. Okay, moving to circular function definitions. When the R value isn't 1. In the last set of formulas that I gave you, I went over each of these formulas. There they were. Let's go revisit them. I went over each of these formulas for circular functions, but I was defining them here in a case where the R value was 1. In other words, your right triangle was going to be inside a circle of radius 1, and therefore the hypotenuse, which is really the radius, was 1. So everywhere that there was an r in the definition here, we were able to replace it with a 1. But if the r value is not 1, you can't just replace it with a 1. You're going to have to hold on to these definitions as they are in their original form. Y over r, x over r, y over x. And then each of these definitions would just be the reciprocal of these. That's why I introduced these. Sure, if you're in this situation, you can replace the r's anytime you have an r by a 1. But now we are looking at these definitions where r is not equal to 1. So we're going to be using this, this, and this. That's why I mentioned them here, because I knew that they would apply further into the section. Okay, so here's those definitions restated in their original form. You may not put a 1 in where you see r's, because the r is not, we're going to be in a case in some of these problems where the r value is just not going to be a 1. Okay, let's take a look at some examples where we can apply some of this information. This says, for any angle theta in standard position, let P be a point with xy coordinates on the terminal side of theta. Picture might be very useful here so you can understand what they're going on about. That is also on the circle x squared plus y squared equal to r. Okay, so what they're talking about is this. Theta at standard position just means the vertex of this angle called theta is right at the origin. Okay, so you're inside of a circle. They don't really tell you what quadrant you're in, so if they don't, I'm just going to draw it in quadrant 1. So you have one arm, just, think about how angles are created. One side of the angle stays fixed upon the x-axis while the other side of the angle rotates. Here's the rotating arm. It digs into the circle. Travel to the nearest x-axis and you will create your right triangle. Okay, horizontal leg is x. Vertical leg is y. This theta that they're talking about in standard position is just an angle with the vertex at the origin, which is where you're standing. The r value, that is the hypotenuse. Okay, now they don't say anything about you being in a unit circle here, so you cannot put r equal to 1. It could be any value for all you know. They're not giving you those values. So they're saying in this situation, how would sine function be defined? It would be defined in its generic form without replacing r with a 1, because you're not allowed to in this case, as just y over r. And how would cosine be defined? As x over r. Okay, so for this first question, that was this one. And for the second question concerning cosine, x over r. And this is just how some of the problems look, where they'll give you multiple choices and allow you to pick which answer is correct. Okay, so number 5, example 5. The point given below is on the terminal side of an angle theta. Again, you have a side that is fixed upon the x-axis while the other side of the angle rotates, and the angle that's formed is called theta. Find the exact value of each of the 6 trigonometric functions. Okay, I'm always going to draw a picture for you so that you can get a grasp of what's going on here. Okay, I'll just do a little one right here. Okay, let's see. I am where x's are positive and y's are negative. So again, one side stays fixed here, and then you rotate to a quadrant where this is possible. You have one arm that's rotating, and this tells you where to rotate to. Where do you rotate to? Again, you always, when you're trying to form an angle, regardless of what it's called theta in this case, you need to know where to take the rotating arm to. And they have told you that by saying this. Go to the quadrant where x's are positive and y's are negative. That would be down here. You can always form a triangle by traveling to the nearest x-axis, which would be you moving up. And you can draw a circle around it if you'd like. Okay, the x, which is always this horizontal leg, is the 12. The y is always the vertical leg of the triangle. It is -9. And the r value, we do not know because you're not in a unit circle. Okay, you have been given no mention of unit circles here, therefore you need to figure out what the r value is. And this theta in standard position, it just means that this is the angle that was created between the fixed side and the rotating side. The rotating side is always the hypotenuse. Okay, and you're going to just use Pythagorean Theorem, which was mentioned very early on in the section. Okay, that goes like this. Hypotenuse form. Hypotenuse squared is equal to leg squared plus leg squared, and you can just plug in what you have and solve for what you don't have. So the hypotenuse is called r. I'm going to square it, and the legs are 12 and -9. Okay, so we're going to go r squared is equal to 144 plus 81. And when we add those together, we get 225. Now the r value, the hypotenuse, can never be negative. Your r value is always positive. This is a statement that means r is always positive. This angle inside the triangle is always positive also. That reference angle that you're seeing there, that's always positive. Just saying something is greater than 0 means it's positive. Okay, so this, we're going to take the positive version of this square root. Because again, when you take a square root on r squared to get r, over here you actually do have a positive and a negative root, but with respect to what we're doing here, the r value must be positive. So it's r is equal to square root of it is 15. So that r value has to be 15. Okay, now that you know what the x value is, the y value, and the r value, you can find the values of all 6 trig functions. So here they are. Okay, so I'm going to do sine of theta, and that is defined as y over r. We can't just use y because that's only in cases where the r value is 1. Really want to make a distinction about that. Okay, must use the r value that you have here. So my y value is -9, my r value is 15. Always reduce your answers, clean up radicals in the denominator, and so forth. So 3 goes into the top 3 times, 3 goes into the bottom 5 times. Okay, so there is your sine value. If you want to go ahead and get the reciprocal cousin right away, you can do that. That would be cosecant. One starts with an S, one starts with a C. And the reciprocal cousins, therefore you can just take this answer and do the reciprocal of it. So that would just be 5/3. Put the negative wherever you want. That's 2 answers. Okay, let's go after the next pair, cosine. Cosine of theta is defined as x over r. X value is 12 here. R value is the 15 that we found. 3 goes into the top 4 times. 3 divides into the bottom 5 times. Reciprocal cousin to cosine, secant. Again, with these first two reciprocal pairs, one of the trig functions starts with an S, the other one starts with a C. Likewise here, just so you don't get them mixed up. Okay, so our cosine value was 4/5, reciprocal of that, 5/4. Okay, now we have 4 answers. Last two, tan and cotan. So tan of the central angle, or the angle in standard position, is y over x. That's the definition of tan. My y value is -9, and my x value is 12. When you reduce that, 3 goes into the top 3 times, 3 goes into the bottom 4 times. There's your negative. And then the reciprocal cousin is cotan. And that would just be this answer in its reciprocal form. Okay, then you have given all 6 trig values. Okay, then we get to example 6. And before we go on to example 6, I want to go over your formulas for special right triangles. This is very much hit upon in geometry, and they'll also talk about it a bit in algebra classes, in your lower algebra classes. And so we really use it a lot here. It is the mainstay of most of the problems that we're going to be doing. So you need to remember those values that go with a 45-45 right triangle and a 30-60 right triangle. So when I talk about the reference angle being 45, that means the theta in standard position. We do refer to that as the reference angle, and when we refer to it in that way, we simply put a little symbol on it that looks like an accent mark. So theta in standard position. That's what I mean when I talk about a reference angle. So if that angle happens to be 45, you're going to have a right triangle with 2 45-degree angles and a right angle. Okay, we're talking about right triangles here. These just happen to be right triangles that we have special formulas for, and you're just going to memorize the values. I mean, I'm going to show you how they come about, how those values come about by using this formula. Any kind of right triangle that's 45, 45, 90, there's only one formula that controls it, and that is that the hypotenuse is square root of 2 times a leg. Now you're in a unit circle for any of these special right triangles. Okay, special right triangle, you're inside of a unit circle. Okay, and then you also have another kind of special right triangle where the angle in standard position is a 30, the other one's a 60. You can reverse those two. That'll just reverse where the short leg and the long leg is. In this triangle where you have two angles that are 45, both of the legs are equal, which I made that comment right here. But here, because the two angles, the two complementary angles, as we call them, because if you have a right angle, the other two add up to 90. So here it would be two angles, both 45 degrees each, that adds up to 90. Here the other two angles besides the right angle would be a 30 and a 60, also adding up to 90. So we always call those a complementary pair. The formulas that rule this kind of right triangle, 30, 60, 90, are these two relationships, which I've stated for you below. Your hypotenuse is always twice as big as the short leg. Your long leg also has to do with the short leg. So if you know the short leg, just double it up, you got the hypotenuse. If you know the short leg, just multiply it by square root of 3, and you have the long leg. These are the two formulas for 30, 60, 90. Okay, we're going to go over that very, very often because that's going to be in a lot of problems. Okay, so for instance, here we go. Let's start getting these two situations to evolve. Okay, the point on the unit circle is theta equal to pi over 4. So you have to learn how to read the command here. They are telling you to rotate. Your rotating arm should rotate to pi over 4. Now, if you want to get a sense of what that is degree-wise, well, you should just know that that is 180. It's the same thing as pi. 180 divided by 4, that means that you are rotating to 45 degrees. 180 divided by 4 is 45 degrees. What is the rotating arm? The hypotenuse is the thing that is considered the rotating arm. This arm stays fixed to the x-axis because we're thinking about how did this angle get created? This angle that's in standard position. It got created by this arm that stayed fixed to the x-axis while this arm, called the hypotenuse, rotated and dug right into the circle. And that's how this angle in standard position gets created. They're telling you that that angle is pi over 4, which is the same thing as 45 degrees. So you are in a special right triangle. Sorry about that snoring. There's my dog snoring while I'm making a video. Okay, so that's 45. This is 90. This pair of angles right here always adds up to 90. So if you have one 45-degree angle in a right triangle, the other one's also 45. That also means this. When you have two angles that are equal, then the sides across from them are equal. Two angles equal mean the sides across from them are equal. It doesn't mean that they're also 45, but whatever this one is, this one is. And then your hypotenuse, well, you don't have to figure that out. You're in a unit circle. Therefore, the radius is equal to 1. So you have this side. And just so you have a little bit of experience working with this formula, I'll show you how you can tell what the value on both of these legs are. But then I think you should memorize it from there. Okay, here is the formula right above. For special right triangle, 45, 45, 90, hypotenuse is square root of 2 times the leg. Hypotenuse, this is always what controls a 45, 45, 90 triangle. So hypotenuse we know is 1 because we're in a unit circle. This is square root of 2. The leg, you could either call it x or y. They're both equal, so it doesn't matter what you put in there. And solve for x. Just divide by square root of 2, divide by square root of 2. Whatever you do to one side, do it to the other side. I think you already know that. And then rationalize it. Don't leave it like that. Let's multiply by square root of 2, bottom and top. So your x value as well as your y value, because those legs are equal, is square root of 2 over regular 2. I think what you should do is memorize that. Just memorize. And this is the one that students typically have no problem memorizing because they're both the same. Whereas when you're talking about a standard angle, your theta being either 30 or 60, then maybe that requires a little bit more work. So now we can do, let's see. The point on the unit circle, all they wanted was the x and the y coordinate. By you finding how long these legs are, that represents this point, because this point that you're seeing right here on the rim of the circle that the hypotenuse digs into has a coordinate of x, y. That means that point is x units out this way. Well, the distance right here is square root of 2 over 2, so that's the x coordinate. And then how high it is up in the air is also square root of 2 over 2. So you have just found the x and the y coordinate by finding the length of either of these legs. And that's all they wanted from you there. They wanted you to find both the x and the y coordinate. If you have the x and the y coordinate, you could go on to find the value of all 6 trig functions at that particular point. They just haven't asked you that in this problem. You have to practice learning how to get the x and the y coordinate and also know the radius in order to find the 6 trig values. But again, they haven't asked you for that here. Okay, let's practice the same thing we did in example 6, only this time our theta is going to be pi divided by 3. So let's get a fix on that. Pi is the same thing as 180 degrees. 180 divided by 3, that's 60 degrees. So this hypotenuse is rotated 60 degrees up in the air. Okay, so now what you have to look at is some of the comments that I have made with regard to a 30, 60, 90 special right triangle. There's your 90, this is 60, therefore this is its complementary partner. If one of your angles is 90, the other two have to add up to be 90. So if this is 60 right here, then that has to be 30. I do want to make a comment that always across from the 30, and if you don't remember this from geometry, which you probably don't, the smaller the angle is, the shorter the side is that's across from it. So the reason the hypotenuse is the longest side is because look at the 3 angles here. There's a 30, there's a 60, there's a 90. 90 degrees is the biggest, therefore across from it is the longest or the biggest side. The smallest angle here is 30, therefore across from the 30 is the smallest or shortest side. And then across from the 60, it being the medium-sized angle of the 3, across from that would be the medium side. So we refer to these legs as the short leg and the long leg. This y coordinate right here, this is going to be the long leg. And I'm going to abbreviate it from now on as just LL. Whereas across from the 30, because these are both called legs, but one of them happens to be longer than the other one. In this case, always across from the 60, you'll have your long leg, and across from the 30 will be your short leg, which I'll just abbreviate as SL. Okay. All right. Okay, so they want to know what corresponds to what. So let's take a look at the formulas that go with 30, 60, 90. And then again, I would like you to memorize the values because I don't want you to have to go through, deriving them each time or solving the equations each time. So the 2 formulas that I gave you right up here at the top of the paper are the following. These apply only to 30, 60, 90 formulas. Hypotenuse will always be twice as big as the short leg. Okay, hypotenuse will always be twice as big as the short leg. Our hypotenuse, we do know what the hypotenuse is. It's 1, so we can put that right there, and then we can just copy the rest of the one equation that we have written so far for 30, 60, 90. You want to know what the short leg is? Just divide by 2. And there you have it. The short leg is always half of whatever the hypotenuse is. And that comes from this right here. If your hypotenuse is twice as big as your short leg and it has a value of 1, then this short leg has to be 1/2. So the short leg is 1/2. That is the length of your horizontal leg, your x value. And then the length of your y value, well, there's another formula that goes with that. And that is also right here at the top of the page. The long leg is just short leg times square root of 3. Long leg is just the short leg times square root of 3. Okay, so here we go finding the long leg, which is really that y value. What was the short leg? Short leg was 1/2. Let me move this down a little bit. That was the short leg, 1/2 times square root of 3. Just hang that square root of 3 right off the side, or you can think of it as square root of 3 over 1, and that would be top times top, bottom times bottom. So this can be written like this, and this is how you'll see me writing it. Okay, but this long leg really comes from one of the two formulas that controls a 30, 60, 90, and you may use these two formulas regardless of whether the 30 or 60 is here. What's going to happen though is if the 30 is here, this will be the short leg, and this will be the other one will be the long leg. That would, if this was a 30 instead of the way it is right now, this would be the short leg, this would be the long leg. But what you can memorize is that the short leg is always the 1/2. And the long leg is always the bigger number. Square root of 3 over 2, which is what we got for the long leg, that is a bigger decimal than this is. This is only 0.5, and square root of 3 over 2 looks like this. It is the longer of the two legs. See, bigger number. That's almost 0.9, and this is only 0.5. So you have a short leg and a long leg. I would memorize those two, but you're going to have to be careful with, hey, does the square root of 3 over 2 go here, or does it go down here? And it's based on this angle right here. What is the angle in standard position? Because that controls what is across from it. Okay, so with respect to the answer for this problem, this point right here is x units over and y units up in the air, and we already know what x and y is. This is y and this is x. So this would be 1/2 for your x coordinate, square root of 3 over 2 for your y coordinate. Moving to example 8. In example 8, it says find the exact value. Do not use a calculator. Trying to get you to have practice with rotating to whatever they have asked you to rotate. Always right next to the trig function. The trig function here that we're concerned with is not all 6 of them, just sine. But this is a comment as to where they want you to rotate to. So remember that when you do a full revolution, this is from section 2.1 where we went over these terms, that's a rotation of 2 pi. Well, if you're going to go to 4 pi, you're just rotating an additional 2 pi, and you are right back here again. Okay, 2 pi and another 2 pi will put you right back here. And look at what the coordinates are, because the x and the y coordinate at any location, and I'm at this location right here called 4 pi. I rotated 2 pi, landed right back there, rotated another 2 pi, landed right back there, and these are the coordinates at that location. As far as what the r value is, you can also see that right there. You are in a unit circle. Now this is what we call a quadrantal angle. A quadrantal angle is when instead of being able to draw a right triangle, you cannot draw a right triangle because you've landed on one of the axes. Okay, a quadrantal angle will make you land either on the x-axis, the y-axis, the negative x-axis, or the negative y-axis. You land on an axis, and therefore you cannot draw a triangle. But that does not stop you from getting an x and a y coordinate, nor recognizing what the r is. I mean, when you're drawing these right triangles through either Pythagorean theorem or by whatever means you're using, you are finding out what x and y is, the length of the horizontal as well as the vertical leg, and you already know the hypotenuse is 1. But when you're in a quadrantal position, just the coordinates at that particular point where you land based on whatever axes you land on, because you can land here, you can land here, but each one of these four locations, whether you're at 90 degrees, 180, 270, or whether you've landed right back here, because sometimes you're going to find yourself spinning repeatedly around this circle, but just landing in those, four spots. Each one of those locations has an X and a Y, and therefore you can get all the trig values using the X, the Y, and the R. So in this particular problem, they did not want all six as stated. They only want the sine value at the 4 pi location. So go get your definition for sine, which is Y over R. Your Y value here is 0. Your R value is 1. Okay, again, your R is just your radius, okay, which is 0. Okay, and that's the answer to that particular problem. Okay, moving on to example 9. Now I've drawn these partially for you just so you could, just to give you a boost into the problem, but you'll be doing it, of course, on your own. When you do it on the test, when you do it in your homework, and you can just reach out if you have any questions. Find the exact value. You are spinning to 60 when you do the sine value and also to 60 when you do the cosine. So just one picture will do. Okay, I've given you a picture of a right triangle where a 60-degree rotation is possible because this is 90. So if you've only spun to 60 with your hypotenuse, again, the rotating arm is this hypotenuse. It is 60 degrees up in the air. Now I just derived the values for you in this situation. Across from the 60 is the long leg. The long leg is always square root of 3 over 2 when you're in a special right triangle with a hypotenuse of 1. The 30 would be this other angle, the complementary partner to the 60. Therefore, this would be the short leg. Short leg's always 1/2. Short leg always 1/2. Long leg always square root of 3 over 2. Okay, now let's go over to the actual problem and complete it. This sine right here is Y over R. My sine value is going to be multiplied by my cosine value. But each of these values, sine and cosine, using a 60-degree reference angle, this is called the reference angle, or you could also call it an angle in standard position. But each of these values have a definition. This is the definition for sine of 60, and we'll actually go and get the values from over here. And the definition for cosine is X over R. Okay, so now all I did here is write the definition, so you could see how you get rid of all the trig name and the angle by replacing it with its definition. So I replaced all of this Y over R, I replaced all of this with X over R. Now I'll go grab the actual X and Y values. The R is just 1. I'll go grab X and Y values off this picture. So it's just Y square root of 3 over 2 over 1. So I'm not going to write that. And X over R would be 1/2 for my X over 1. So I'm not going to write that. Multiply top times top. Bottom times bottom. And that's your final answer. Okay, moving on to example 10. In example 10, it says find the exact value. I've provided you with two different places to put your values because you're talking about two different angles here. Okay, you might want to get a fix on what they're talking about with respect to this pi value here. Maybe think in degrees. That's probably going to help you to figure out which of the special right triangles you're dealing with. 180 divided by 6, that is a 30-degree triangle you're talking about. So we're going to want to know what the sine on a 30-degree triangle is. Ultimately, we'll be multiplying it by 2. Then we're going to subtract 6 times tan of a, again, this is 180. Pi is the same thing as 180 divided by 4. You're talking about a 45-degree triangle. Those are the two triangles that we're going to draw here. Okay, here we go. Sine of 30. Let's let this one be my 30-degree triangle. Therefore, this would have to be the 60. Always across from the 30 is the short leg. Short leg is always 1/2. Always across from the 60 is the long leg. And the long leg is square root of 3/2, a bigger number than that. Thus the name short leg, long leg. Remember your vertical leg, we call it Y. The horizontal leg, we call it X. So the Y always has to do with the sine, and the X always has to do with the cosine. Let's make a picture for this, 45. So this would be 45, and therefore its partner is also 45 because these two have to add up to 90, just like these two did. Okay, in this case, both of the legs are equal. This vertical leg as well as the horizontal leg, and if you remember from the problem I did previously in this section, both legs turned out to be square root of 2/2. I would memorize these values. They are going to come up constantly. Notice that I'm not messing around with any negatives because I'm in a quadrant where both x's and y's happen to be positive. So I have not attached any negatives, but we do have to be cognizant of that as you rotate from one quadrant, if you do happen to leave quadrant 1, we haven't done so yet, then you have the possibility of either your x or your y value being negative or possibly both, depending on what quadrant you're in. Okay, so we have what we need to finish this problem. So we're going to bring this information down to, notice that once again, here I come replacing the trig name and the angle with its definition. Sine of anything is defined as y/r. Oops. Multiplying or subtracting 6 times my next value. Okay, so that's 2 times. I'm going to do sine of 30 right in there, and then I'm going to go minus 6. And then let's see, definition for this trig name with its angle, y/x. These fractional names get rid of the trig name and the angle that's with it because we've already drawn pictures for all of this. Okay, so here we go. Now going to the pics that we've created. Okay, so I'm trying to work with my 30-degree picture. That would be this one. And my y value, I'm trying to get my y value over my r value. My r value is just 1 in this case, as well as this case. The r value is just the hypotenuse. So when you do y/r, you're really just doing y. My y value is this up and down leg, 1/2 over an r value of 1. And then my y/x, well, let's see. I'm supposed to be doing y/x for this 45-degree situation where I was doing y/r for the 30-degree picture. So if I'm going to do y/x, I mean, I'll write it out, but it's your y value is your vertical leg divided by your horizontal leg, and they just both happen to be the same. So this is 1. So more simplified, this would be 2 times 1/2, 1, minus 6 times 1, which is equal to 1 minus 6, which is equal to -5. Okay, moving to example 11. Find the exact values. Notice that almost every single one of these problems, well, I think every problem we've done thus far has said find an exact value, which means you may not use a calculator unless you've been instructed to approximate or actually use your calculator in the definitions. Okay, this time we're moving out of quadrant 1. And that's why this picture, I've already prepared it for you, but you're going to be doing it yourself when you create it yourself. We're moving out of quadrant 1. Okay, so let's start getting a fix on how do I determine what quadrant I'm in. It takes a little bit of knowledge of how to count in fractions. All right, first of all, if you were to rotate from here to here, right to this location, that would be called 1 pi. Notice that we are talking sixes. You have a denominator of sixes. And because you have a denominator of 6, I want the denominator at this landmark. This is an important landmark, 1 pi and 2 pi, because it helps us with knowing where to rotate to when the rotation is left up to the student. I did it for you. So I'm trying to explain to you why I stopped in quadrant 2. Okay, we're talking sixes. How many sixes is equal to 1 pi, which is where I'm at? 6 sixes. So if this hypotenuse is my rotating arm and I wanted to rotate to 5 sixes, you just look at the denominator, restate the landmark that you are headed for by having this rotating arm rotate to 5 sixes. You want to use that denominator right there. The top should match it if you're trying to create a 1. So 5 sixes would have had to have been from here all the way to here. That's what you're talking about, 5 sixes. So let's think about this. If I had rotated right to here, and that was 5 sixes, rotating all the way to there, I just labeled it up here. How many sixes would be left right here? So this is your first exposure to reference angle. Because when you're in quadrant 1, as all the problems have been up to this point, this reference angle, notice they're using a little accent mark now. The reference angle in quadrant 1 is the same as how much you've rotated. So the student is not pushed into thinking this. But if you've rotated 5 sixes, what is the difference? Which is what this angle is. This angle called the reference angle in standard position with its vertex at the origin. Okay, 5 sixes plus 1 6 would be 6 sixes, because these arcs are the same as the angles that they correspond to. If this is 5 sixes, then from here to here is 5 sixes. If this is 1 6, then that's 1 6. So basically what's happening here is rotated with my hypotenuse to 5 sixes. What's left from here to 6 sixes would be 1 6. And that is where this reference angle comes from. That is probably the most significant thing in the class. It comes up in every single chapter repeatedly, over and over and over again. So we're going to try and get real good at figuring out the reference angle. Again, all I did was think about this 1 pi in terms of sixes. I called the 1 pi location 6 sixes. I had rotated to 5 sixes as requested right here. But that meant that I needed to figure out, based on that rotation of 5 sixes, what was left over from where I stopped my rotation to here. That is 1 additional 6 right in there. And whatever this is, that's what this is. Whatever the arc is, that's what the central angle is that corresponds to it. So that's 1 6. That is the same thing as 30 degrees. You'll probably get good at doing that in your head, but if not, put it in your calculator. 180 divided by 6, 30 degrees. Therefore, this leg right across from the 30-degree reference angle has to be the short leg. Short leg's always 1/2. This would have to be the 60-degree partner. Always across from the 60 is your long leg, which is always square root of 3/2. Your hypotenuse is 1. Your cosine is equivalent in these cases to just x. I mean, it is defined as x over r. But if the r is 1, then cosine is equivalent to x, and sine is equivalent to y. Okay, let's continue here. Find the exact value of all 6 trig functions. So if we're going to do all 6 trig functions here, that means we can use these values that are right on the right triangle and get all 6 of them. So it's sine based off of a rotation to 5 pi over 6. Always state what that original angle was. This was your original rotating theta, which led us to be able to figure out what this reference angle is. And now we have definitions for each of these. Sine of any angle is defined as y over r. Y in this, just y in this case, just because the r happens to be 1. And the y value here is the vertical leg, 1/2. Okay, reciprocal cousin. It's the reciprocal of that answer. So cosecant, everything's about the triangle that was built based on a rotation to 5 pi over 6 leading to this reference angle. But the definition for cosecant, well, it's defined in the reciprocal as the reciprocal to the sine. So it would just be 2. So I have 2 answers here. Next I go to cosine. Cosine for any angle is defined as x over r, but in this case, since the r is 1, it's just x. That x value is the horizontal leg. Square root of 3 over 2. Okay, reciprocal cousin to cosine, secant. Okay, just a reciprocal of this, 2 over square root of 3. If you happen to get an answer once you flip it over that has a radical in the bottom, do rationalize it. See, if you're putting any part of this in the calculator, you are not showing that you have learned anything regarding the definitions for the trig values, nor are you going to be able to show any of the algebra, and you will lose all the points for that portion of the problem, because it's all about being able to support your answers once you start taking any mathematics courses in college. So make sure that you are doing it the way the lectures have instructed you. Okay, here if you complete this, this will be 2 times square root of 3 over 3. And there you have your 4th answer. Okay, last ones are the tangent and cotangent. So it's tan of any angle is defined as y over x. And our y value in this case, again, is always the vertical leg. I have to work for this one a little bit. And the x is the horizontal leg, which has square root of 3 over 2 on it. Then we have a complex fraction here, so we're going to float and flip. Float that divisor up to the top, flip it over. These 2's cancel, leaving you with 1 over square root of 3, which would be good if we took radicals in the denominator, but those are not acceptable. So multiply by square root of 3, square root of 3. And it is square root of 3 over 3. That's your 5th answer. Then the reciprocal cousin will just be, I could use the reciprocal of this, but then I'm going to be right into a situation again where I'll have a radical in the bottom. So I'm going to back it up a little bit because there are other things that are equivalent to this. So I'm going to back it up to what it looked like before I did this rationalizing step. It was an answer that was 1 over square root of 3. How about if I just flip that? Okay, because 1 over square root of 3 is equivalent to this. You'll actually get the same exact decimal for both of these. It's just that this is considered simplified algebraically. This one's not, but they are equivalent. But this would be good for purposes of which one would be better to flip over. I'm going to flip over this one, and it'll just be square root of 3. Okay, then you have all 6 values based on your rotation to 5 pi over 6 and what that 5 pi over 6 yielded with respect to this reference angle, because it's really the reference angle that ends up giving you the sides of the triangle, and the sides of the triangle get all 6 of these answers. So it's a process. Okay, moving on to example 12, where this time we are going to rotate multiple times around the circle. You might want to think about, I mean, it's up to you. You can just turn it into a degree if that makes you better able to figure this out. Yeah, you could have even done that with the last one that I did if that's easier for you. But I'm not going to stop going over with how do you help yourself count in fractions. But I'll do this one where I just pop a 180 right here. So this would be the same thing as 17 times pi. If I wanted to do it in degrees, well, then I would call pi by its degree type name, 180. 180 degrees divided by 4. So that would be equal to 17 times 180 divided by 4, and that would be 765. Okay, I want to rotate to 765 and figure out what the reference angle is. Rotate to 465, to 765, then figure out the reference angle. This is the main theta here that you're going to rotate to. Okay, so let's rotate to 765. Now I think we all know and are very comfortable with the fact that one spin around the circle is 360. How about 2 spins? Even 2 spins are not going to get us all the way to 365. 360 times 2 is 720. That won't quite get us there. We would still need to do an additional 45. So here I am at 360, spin around again, you're at 720, and then you need an additional 45 degrees to truly be at 765 degrees with this spinning arm. Okay, one more time. I went around once, that was 360. I went around twice, that was 720. I was trying to get to 765. So once I got to 720, I needed an additional 45 degrees. Well, if this is 45 degrees right here, then this is 45 degrees. This arc on the edge of the circle corresponds to the angle in central position. And this is what we call the reference angle associated with that type of spin. Okay, this is 45 degrees, and being that it's 45 degrees, so is this one up here. These two partners must add up to 90. So you are in a situation where this leg and this leg are the same, and they are both square root of 2 over 2. You're in quadrant 1, so absolutely nothing is negative. And I want to look over to this previous problem. Before I finish this one, let me just take a quick look here. Yep. I will have to go and fix some of the signs for this problem. I might as well do it while I'm here. When I went to do this problem for 5 pi over 6, so please fix this in your notes. This was 1/2, but since I'm in this quadrant, this needed to be negative, and I believe I left that off of there. That needed to be negative. So anywhere that you use that square root of 3 over 2, just pop a negative on there, and we can do that together real quick before we go and finish that other problem. So cosine, this should have a negative in front of it. This came from using... it was just this flipped over, so this is going to have a negative. Here there was a negative down here, So positive divided by negative is negative. Please put those negatives in there. And then, let's see. So all of this would have been negative. And this would have been negative. Please excuse that and please fix it. Okay, so those are corrections made to example number 11. Glad I caught that before I got done with the video. Okay, so for this one that we had started where we rotated to 765 and then we were figuring out what the reference angle is. We're in this quadrant, in quadrant 1. Nothing can be negative here. Not the x's nor the y's can be negative. This is just a little hatch mark on the side. So you actually have your x value, which is this leg right here. I'll just remove it from the picture, is positive square root of 2 over 2. And you also have your y coordinate, which is positive square root of 2 over 2. In this quadrant, both x's and y's are positive. Okay, so let's see. What do we have to do here? We're looking for all 6 trig values. So when we go and find all 6 trig values, we know that r is 1 in this special right triangle that we're in, and we can find all 6 trig values. So it's sine of a 765 degree rotation, which really resulted in a 45, 45, 90. See, all these rotations that you're doing, you're going to end up in either a 30, 60, 90 or a 45, 45, 90. Okay, we have the same definition we always use for sine, which is y over r, but since r is 1 in this case, it's really just all about the y value, which was square root of 2 over 2. I've written it here as well. Okay, reciprocal function to sine is cosecant. Okay, this came out square root of 2 over 2, so this would be the reciprocal of this, which needs rationalizing, so we'll have to get rid of that radical in the bottom by doing this. 2 square roots of 2, 2 times square root of 2 on the top, regular 2 on the bottom. These cancel so that your cosecant value ends up being just square root of 2. Okay, so we have the sine, we also have the cosecant. Then moving on to the next 2 values, we have cosine of 765. Definition, just really going over these definitions with you, x over r, but r is 1 and therefore it's really just the x. And so you see we're going to get all the same values because y is square root of 2 over 2, so is x. And if that's the case, then the reciprocal of cosine is going to come out the same as the reciprocal of sine. So there's no need to do all that work all over again. After all the simplifying, we got square root of 2, so this one's going to come out the same. Okay, we have a third and a fourth answer, cosine and sine. Then as far as tangent goes, I don't know that you really need to show all the work for this. I think you can see that this is y divided by x, but yet the y value and the x value are both the same. Anything divided by itself is 1. If you want to not show the work for that particular one, just when it's a 45, 45, 90, it's okay. When it's a 30, 60, 90, I need you to show the work. And then the cotan would just be the reciprocal to this answer, which is x over y, get you the same answer when you flip it over. So both of these turn out to be 1, and there you have all 6 answers for a 45-45 triangle, which resulted from a rotation of 765. Okay, in number 13, this one says find the exact values of the 6 trig functions of the given angle. This time we are rotating to 405. So if you're rotating to 405, you may want to judge that based on 360. One full revolution would get you to 360, and then the difference between 360 and 405 is an additional 45-degree rotation, which would finally get you to 405 degrees. But whatever that additional rotation was to get you from 360 to where you are up in the air right here, that extra 45 degrees is also what this is. So you are right back in the same situation that you were in this diagram above, with both this leg being square root of 2 over 2, the y value, as well as this x value being square root of 2 over 2. So both x and y, both of the legs, are square root of 2 over 2. You're in quadrant 1, so nothing is negative, and this r value is 1. Alrighty, so now this one also says do all 6 trig values, but aren't we going to get all of the same answers that we got right here? Because whether you spin to 765 or whether you spin to 405, what matters is what kind of triangle you create, regardless of where you spun to. If you created a 45, 45, 90 here, as well as here, you have to get all the same answers. So sine of 405, I'm just going to copy those answers, is going to be sine value in the problem right above this, which resulted in the same exact type of special right triangle, r value of 1, and then both legs square root of 2 over 2. So I can't help but get it all the same answers. It's just that I'm going to report this angle right next to all the trig words as 405. And you could even put these in your calculator, and you would see that you get these same. It's just that you're not allowed to give them like that, but just to kind of use your calculator as an answer key. So that was the sine and the cosecant value in the problem above. The cosine in the problem above was also square root of 2 over 2, and its reciprocal partner, same thing, square root of 2. And then both tan and cotan turned out to be 1 in the problem right above this, and I went over the reasoning why. Okay, so a lot of the same type of problem, rotating to an angle, figuring out what the reference angle is, attaching negatives to any kind of x and y value, if that be the case, which was the case in the one that I corrected. There was some negatives because I was in quadrant 2, and that was example, that was all the way back in, let's see, example 11, I believe it was where I corrected those negatives that I left out of there. Okay, so in this problem, example 14, we're almost done here. We're right back to a quadrantal angle situation. I will not be able to draw a triangle because I'm going to land right on one of the axes. Okay, so let's work this here. Every time you go 90 degrees, that is a half of a pi. So this is half a pi, 2 halves, 3 halves, 4 halves, 5 halves. This is the same thing as 5 halves when you land right here. Okay, once again, that was a rotation of half a pi, 2 halves, 3 halves, 4 halves, 5 halves. If you do want to put that in degrees, you're just going to see that it is full rotation of 4 halves or 2 pi plus 90 more would be 450. So 360 plus 90 more. This is the same thing as 450 degrees. It's just 360 plus 90 more. So when you're at this location, again, what you're really grabbing once you get done spinning to a particular location, we just spun to 5 pi over 2, is grabbing the x and the y or calculating it yourself. If you're inside a special right triangle, those special right triangle formulas, the values that I had you memorize, because we're actually not going to use the formulas each time, that's what gets you x and y. But when you're at a quadrantal position, in other words, right on an axis in a unit circle, then you're talking about all zeros and ones. X coordinate is 0, y coordinate is y, and of course the radius is 1. And it's nothing more than x's, y's, and r's that get you all 6 trig values. That's what you've been asked to do again, get all 6 trig values. So it's sine of whatever angle you're rotating to has a definition of y over r, but since r is just 1, it's just y. So we want the y value. That value is 1. And you could even put this in your calculator. If you're feeding in a radian type number, radian means a decimal type number, pi is a decimal type number, your mode would have to be in radian. But if you did feed this into your calculator, you wouldn't get the points for showing the work. I need to see that you know that you rotated there, that you understand what the x and the y coordinate is, and that that's why you are picking this. But if you put in your calculator, you will get a 1. All right, then reciprocal cousin to sine is cosecant. So reciprocal cousin means you just reciprocate that answer, but when you do reciprocal 1, you still get a 1. Cosine at 5 pi over 2 would be x over r, or just x. And so when you do you can do it like this if you want to, but you can just write it as just x because your r is 1. So x over 1 is just x. X value at this particular location, 5 pi over 2, is 0. Okay, so reciprocal cousins. See, sometimes it's easier for you to understand other answers by paying attention to not the most simplified thing, but maybe this definition. Okay, if you were to use the x and the y value to get this 0, because you would still get a 0 whether you use just x or whether you use x over r, it would have been 0 over 1. Well, when you take that now and do the reciprocal, because this is the reciprocal cousin to cosine, then you have 1 over 0, and that means secant is undefined at 5 pi over 2. Okay, so at this particular location, the secant is undefined. Then going in for the tangent at 5 pi over 2 with its usual definition, y over x. Y over x at 5 pi over 2 would be 1 over 0. This is the y, this is the x. So the tan is undefined at 5 pi over 2. And then cotan, well, cotan would be the reciprocal of this. Instead of y over x, it would be x over y. Or just take the answer that you were working with, this 1 over 0, flip it over so that you have the reciprocal. Now that's equal to 0. It's just that when the 0 is on the bottom, it's undefined. So the secant was undefined, the tan's undefined. But the cotan we actually have a value for, and that value is 0. Okay, so those are our answers, all 6 answers. 2 of them came out undefined. And then there's the problems where you're just putting it in the calculator. And I have made a little comment for you that if you're going to use your calculator to approximate trig values rather than do what we've done in 99% of this section, which is to give exact values. Because with exact values, you need to pull out the formula, do some drawing in certain cases, and then show that you know how to do the simplifying steps that you were taught in your lower algebra courses, but continue to practice now. Calculator, you're just letting the calculator do everything. You don't need to know a formula. You don't need to know how to simplify. You're just getting a decimal. That's why you cannot give me that kind of answer when the problem says give an exact value. And you can assume that the question is asking for an exact value unless it says approximate or unless it says use your calculator. That's the same thing. Okay, I wanted you to notice that your calculator has a mode button, and the mode button is determined by this argument. This is called the argument, whatever you are finding the trig value for. So if it is in degrees, then the mode should be in degrees. If it's in radians, any type of decimal argument, which this is, pi is a decimal, then the mode needs to be in radians. Okay, obviously that's a decimal, obviously that's a decimal. The trick with these two is that there's actually no key for cotangent or cosecant, so I'm going to show you how to use the keys that you do have on your calculator to get cotangent and cosecant. So sine of 58, just a matter of you making sure the mode is okay. So mode key is second column, second key down. Mine's in degrees right now, so I'm going to quit out of there. Just press second, quit. Okay, and then go ahead and feed it in. Sine of 58, and it becomes point. And this we're rounding. Let's round to the hundredths place here. They'll tell you in your online software what place to round to. So I'm going to round to the hundredths place. So that came out to be approximately 0.85. Then this one here, this is a radian type number. So you're going to change the mode to radians. So mode, click on radians, press enter. Now after you've made that selection by pressing enter and it's blinking on the mode you want it in, push second, quit. So this is going to be tan of pi divided by 12, close it up, and there's your tan value, 0.27. Okay, then here you don't actually have a key, but remember that this is the reciprocal to tangent. Cotan and tan are reciprocal cousins. So knowing that this is related to tan, you can write it as the reciprocal of tan. This is another way of writing reciprocals. 1 over whatever you're the reciprocal to. Because we do have, so we can actually press it in the calculator like this, 1 over tan, and that argument right there goes right here. It's 0.1, 1496, 1496. So 1 divided by tan of negative 6.1496. And that is 7.44. Okay, then we're going to cosecant. Cosecant is the reciprocal of sine. We're doing 6.8612. So it's 1 divided by sine of 6.8612. Close that up. And we have 1.83. And that is the cosecant of 6.86. That's equivalent to this. 1.83. Okay, that concludes section 6.2.